You know, machine learning, it really does feel like magic, doesn't it? I mean, we've got models that can see, that can write, that can create amazing art. But you and I both know that behind that curtain, it's not magic at all. It's math. And yeah, that math can feel like this huge, intimidating wall. But here's the thing. What if there was a map to get over it?
So, what's the real secret here? Look, it's not just about knowing which library to import or which function to call. The real secret, it's about understanding the engine. It's about getting a feel for the core mathematical ideas that give these algorithms all their power. And that's exactly what we're going to dig into.
Seriously, I'm not exaggerating when I say this. Understanding the math is a superpower. It's what separates someone who just uses ML from someone who can actually innovate with it. You know, someone who can really get under the hood, troubleshoot when things go wrong, and push the boundaries of what these things can do.
And look, if you've ever opened a paper or a textbook and just felt completely overwhelmed by all the Greek letters and weird symbols, you are definitely not alone. I think we've all been there. These brilliant ideas are so often hidden behind layers of really dense, abstract math. But here's the good news. The core concepts, they're actually way more intuitive than you might think. You just need the right map.
So here's our roadmap for today. Pretty simple. We're going to start with the big picture, the 3 pillars of ML math. Then we'll take a quick tour of each one, that's linear algebra, calculus, and probability, and see what they're all about. And finally, we'll talk about what your journey looks like from here. All right, let's get into it. The first step in tackling any huge, intimidating subject is to break it down. And that's what we're going to do. We're going to see that this whole world is really built on just 3 foundational territories.
That's it. Just 3. Not 20, not 50, just 3 core ideas. Kind of makes the whole thing feel a lot less scary, right? Suddenly it feels, well, manageable.
And here they are, the big 3. Linear algebra, calculus, and probability theory. I'm telling you, everything in machine learning, from the most basic linear regression to the craziest, most complex deep learning model, it's all built on top of these 3 pillars.
So how should you think about what each one does? It's actually pretty straightforward. Think of it like this. Linear algebra, that's the language we use to describe our data and our models. Calculus, that's the engine that does the work, that actually fits the models to the data. And probability, that gives us a way to deal with all the messiness and uncertainty of the real world.
Okay, first up, Pillar 1, linear algebra. Now, forget whatever you might remember from high school about solving for x and y. In the world of machine learning, linear algebra is something much cooler. It's the language of data. It's how we represent and manipulate information. And in this language, there are 2 key words you've got to know: vectors and matrices. Think of a vector as a single data point. It could be a list of features for one of your customers, or maybe all the pixel values for a single image. It's a thing. A matrix, on the other hand, that's an action. It's an operation, like one layer in a neural network, that takes that vector and does something to it, stretches it, rotates it, squishes it. So a vector goes in, the matrix acts on it, and a new vector comes out. Okay, so then you hear words like determinant, and it sounds super abstract and scary, right? But the idea behind it is actually beautiful and simple. Just imagine a little 1x1 square. When you apply a matrix to it, that square might get stretched into a big parallelogram or squished into a tiny one. The determinant? It's just a single number that tells you how much the area of that shape changed. That's it. It's just a measure of how much that matrix scales space.
All right, pillar number 2, calculus. So, if linear algebra gives us the blueprints and the parts for our machine, calculus is the powerful engine that actually makes it learn. This is the mechanism that drives the whole process.
And right at the heart of this learning engine is this one crucial idea, the gradient. The best way to think about it is to imagine you're a hiker, lost on a mountainside in a really thick fog. You can't see anything, but your goal is to get down to the bottom of the valley. The gradient is like a magic compass. At any spot you're standing, it points you in the direction of the steepest way up the hill. So if the gradient points uphill and we want to go downhill, what do? It's simple, right? We just take a little step in the exact opposite direction. And that's it. That's the core idea of gradient descent. You figure out which way is up, you take a tiny step down, and you just repeat over and over and over until you're at the very bottom.
Now, here's the kicker, the really important part. That hill you're walking down, that's not a real hill. It's a landscape representing your model's error, how wrong it is. We call it a loss function. So the bottom of the valley is the point where the model makes the fewest mistakes. This whole process, this gradient descent, is literally how a neural network learns. It's just a fancy way of taking tiny steps
to minimize its own errors.
And that brings us to our third and final pillar, probability. Look, the real world is messy. It's not neat and tidy. It's full of randomness and uncertainty. Probability is the toolkit that lets our models deal with that mess. It's the framework for making smart guesses when you don't have all the information.
Let's talk about a coin flip for a second, because it actually reveals a super common misunderstanding about probability. We all say, oh, it's a 50-50 chance. But what that 50% probability doesn't mean is kind of the most important part.
It definitely doesn't mean that every other flip will be heads. And if you get, say, 5 tails in a row, it doesn't mean the next one is due to be heads. That's a classic trap called the gambler's fallacy. The real meaning of probability is all about what happens in the long, long run.
And this is where a cool idea called the law of large numbers comes into play. All it says is that if you do something a ton of times, like you flip a coin 1,000,000 times, the final count of heads is going to be incredibly close to 50%. See? Probability isn't a prediction about the next flip. It's a guarantee about the average result over a huge number of flips.
And this idea of a long-run average has a name: expected value. And this is a huge deal in machine learning. Remember that error, that loss function we were trying to minimize with calculus? Well, a lot of the time, that loss is actually defined as an expected value. We're trying to find the model that has the lowest average error across all the possible data it could ever see.
So there you have it. That's the map. The 3 pillars. Linear algebra is the language, calculus is the engine, and probability is the guide for dealing with uncertainty. You now see how it all fits together. The map is in your hands.
There's this quote that I think just perfectly sums this all up. It says, "I will show you the road, but you must walk it." And that's really what this is all about, right? We can give you the map, we can point out the big landmarks, but the real learning, that deep intuitive understanding, that only comes from walking the path yourself. And that was our whole goal today, to hand you that map, to show you that this isn't some huge tangled forest. It's 3 distinct territories, and now you know what they are and how they connect. You're not lost anymore. You've got a compass.
So I guess there's really only one question left. Where do you want to start? Are you going to dive into the language of data with linear algebra, tinker with the engine of learning in calculus, or explore the framework of uncertainty with probability? The choice is yours. The journey starts now.